This is an introduction to the Humidity and Adiabatic Process Lab, lab number 4. So this lab deals with parts of the water cycle that you see here. All of the water on Earth cycles through these processes, and we have condensation that is happening from evaporation of ocean water, and we have transfer of water through the atmosphere, which interacts with the land in forms of precipitation. There is ice and snow as one type of precipitation, rain, fog, and dew, mist. All of those are classified as types of precipitation. When water is deposited on the land, either frozen or in liquid form, it is subject to snowmelt runoff, stream flow, surface runoff, and other types of processes that will bring the water either down into ground flow and ground storage, or eventually back down into the oceans, the portions that are not evaporated directly into the atmosphere. And so we're going to be looking at the concept of humidity. And when we talk about humidity in this lab, we're not talking about how it feels when it's humid in the weather. This is a scientific concept. It's important for you to know the definition that relative humidity equals the actual water vapor content divided by the water vapor capacity. So it is a mathematical expression. It's a ratio. And this symbol here is a fraction. It indicates that there is a division process. And this expresses the degree of saturation as a percent. So you want to think about actual water vapor content, how much water is there that can be measured. And then water vapor capacity, how much can that parcel of air that we're studying hold. Relative humidity is also defined in our lab as mixing ratio divided by the saturation mixing ratio times 100. You will be given charts and tables that have information, either they include the saturation mixing ratio or the mixing ratio, or they give you a means for discovering that. And you will see on page 110 of your lab manual that there are charts that you will use. So saturation mixing ratio is the water vapor capacity of air at a given temperature. The mixing ratio is the water vapor content. So now we have two different definitions for the same term, relative humidity. I want to give you a visual to think about. So if we think about a plastic water bottle, the actual amount is what you can measure, and that would be the part in the numerator. And the capacity would be how much that container can hold. Now, when we talk about mixing ratio and saturation mixing ratio, this is just another way to calculate relative humidity, and you will be doing both in the lab. So let's think about this idea of measured amounts of water versus the amount that it can hold. I just talked about a plastic water bottle, but I want you to consider this diagram here, and these circles are representing water vapor in blue and a parcel of air in yellow. Now, we tend to think of air as not having substance or mass, because we don't really feel air very much as humans, but air does have mass and it has a capacity to hold water. So if we look here, all three of these circles are the same size, and that means that the water vapor is the same in these three examples. If we start in the middle, you can see that the blue circle is smaller than the yellow circle, and this is indicating that there is more capacity than water vapor in this example. In fact, there's 52% of water that would be in this parcel of air. 100% would be saturation. If we look over at the left, we see that you can't see the yellow circle, and that means that this air parcel is completely saturated or it's completely full. The example on the right, the air could hold even more water, and so that same size of water vapor that we had in the first two examples is representing 28% of the water needed for saturation. Few more points in this diagram. This is representing that air changes how much water it can hold, and that corresponds to temperature. So there's a direct relationship. Higher temperatures, this example here is 30 degrees Celsius, can hold more water before they get to saturation than lower temperatures. So this same water vapor is 28% at 30 degrees Celsius. It's 52% at 20 degrees Celsius. If that same air drops down to 10 degrees Celsius, it's 100% saturated. At saturation, that is the point when precipitation occurs. And then these images up above are just to show you examples of climates that would have low humidity versus high humidity on the right, where you can see the fog in the air, and this would be a tropical rainforest. Same concept with different images, and so warmer temperatures increase the amount of water vapor that can be in the air. This diagram, or this object here in this diagram, represents water vapor in the air. As the temperature goes up, this parcel of air can hold more water before saturation occurs. So there's something about saturation, it's 100%. That means the numerator and the denominator are the same value. On the right, this is just a representation that cooler temperatures decrease the amount of water vapor that can be in the air. Less water vapor in the air decreases humidity levels. So let's think of this cube as a parcel of air. So at 0 feet, we have a temperature of 78 degrees. The dew point is the temperature at which saturation would occur. And so let's look at the definition of dew point, or dew point temperature. It's the temperature at which dew forms and is a measure of atmospheric moisture. So dew forms at saturation. It is the temperature to which air must be cooled at constant pressure and water content to reach saturation. So if the pressure doesn't change and the water content doesn't change, when you get to the dew point temperature, you have saturation. So going back to our cube over here, the dew point temperature at 0 feet or sea level would be 58 degrees Fahrenheit. If we go up to 1,800 feet, we know that the temperature is going to cool as we go up in elevation, going up this hypothetical mountain. Now, the dew point temperature is 58 degrees Fahrenheit. That means if the ambient or surrounding temperature drops to 58 degrees, the water in the atmosphere will form a dew or come to precipitation because it's saturated. Even higher, at 3,600 feet, we have a dew point temperature of 58 degrees. You'll notice that there is now a cloud in our cube, and that's indicating that the temperature has dropped to 58 degrees. The dew point is 58 degrees, and so now we have condensation. Also notice that these cubes get bigger because air expands as you go up in altitude. So here we have identical boxes with identical amounts of water vapor inside. The difference is the temperature. And so if we start over at the left, we have 70 degrees Fahrenheit. The amount of water in this box represents 40% capacity. If the temperature drops to 50 degrees Fahrenheit, now we have 80% relative humidity. If the temperature drops even further to 43 degrees Fahrenheit, now we've reached 100% relative humidity. So those two equations that we talked about earlier would have the same value in the numerator as in the denominator. Anything lower than 43 degrees Fahrenheit and you are getting the inside surfaces are showing dew or evidence of being wet. And so if we go to the left, we have increasing temperatures. If we go to the right, we have increasing relative humidity. So dew point temperature, again, is the temperature at which a parcel of air reaches 100% relative humidity. The temperature at which the saturation mixing ratio equals the mixing ratio. As well, it's the temperature where the actual water content equals the capacity of the air to hold that water. This here is a chart showing you dew point, nothing to memorize here. And these are the human perceptions. Now, I talked initially about this being a scientific lab, and so humidity is shown here, and that's the human perception. Relative humidity is shown here, and it is a percentage or a ratio. So that's the difference. When you talk about humidity, you're usually talking about weather conditions and how people feel in those different kinds of weather conditions. Relative humidity is a numerical value. You're going to be looking up information that was collected with the psychrometer, and so there are psychrometer tables in your lab. Now, the way that you read this chart is that here along the first column is the dry bulb temperature, and you will be given word problems. I'm going to go through how to approach solving word problems, and you will use information about the dry bulb temperature. You're also going to use information about the difference between wet bulb and dry bulb. And so you would find the difference between these two values, and then you look up and cross-reference the dry bulb temperature. So in this example that I've highlighted in blue, let's say that we had a wet bulb temperature of 34 degrees Celsius and a dry bulb temperature of 24 degrees Celsius. 34 minus 24 is 10. You come down until you cross-reference the 24 degrees dry bulb temperature, and the way that you find the dew point would be where those two, where the column and row intersect, and it would be 6. So if the wet bulb temperature is 34 degrees Celsius, dry bulb is 24 degrees Celsius, that's a difference of 10. Come down until you find 24, and that gives you the dew point, which you can find in the title of the table. You're going to be looking at the adiabatic process in lab. It's defined as the way that a parcel of air cools enough to form clouds and precipitation. When we have a dry rate, it's 10 degrees Celsius for every 1,000 meter elevation change. If it's a moist rate, it's a 6 degrees Celsius change for every 1,000 meter elevation change. And so this is referring to the phenomenon of air parcels moving up or down in the environment. Notice here on the y-axis that we have altitude, and this is meters above Earth's surface. These are units of 1,000. On the x-axis, we have differences in temperature. And again, the difference between these two rates is that one is a dry rate and one is a moist rate. Where the environmental conditions change from dry rate to moist rate is called the LCL, or the lifting condensation level. So at the LCL, or the lifting condensation level, that is where the clouds are forming, and that is our condensation. It depends on the moisture of content of air that is being lifted and the altitude, usually expressed as a pressure. In this example here, it's shown in a measurement of meters. So when a parcel of air is lifted, you can see that we have a rate change of 10 degrees Celsius for every 1,000 meters. So we start at the surface, which is 0. We go 1,000 meters. The temperature went from 32 degrees to 22 degrees Celsius. So that's a 10 degrees Celsius change. If we go another 1,000 meters in height, we have another 10 degree change, and we go from 22 degrees Celsius to 12 degrees Celsius. Going up another 1,000 meters, we have another 10 degree change from 12 degrees Celsius to 2 degrees Celsius. Something happens at 3,000 meters, and that's because it's the lifting condensation level, and now the rate of change is actually 6 degrees Celsius per kilometer. And so in the diagram and your lab, you're using different rates. So this one uses 5. So 2 minus 5 is minus 3. And then a minus 3 minus 8 is, minus 3 minus 5 is a minus 8. So here's the way to step back and think about this. If you are having a dry adiabatic rate, you are changing the temperature 10 degrees Celsius for every 1,000 meters of change. If it's a wet rate for your lab, I want you to use 6 degrees Celsius. This image uses 5. They're very close, and it's just complicated physics that we won't get into. Use 6 degrees Celsius for your lab calculations.